Har han något ljud där framme?
Nej,
slå på.
Ska vi skita?
Ja, skit det. Kör. Kan du få igång ljudet? Olle! Det är okej.
Oh, I hear myself.
Okay, so we had a bit of a mix-up here. The speaker that was supposed to go on didn't know that we were running early, so he's out on the town and he couldn't find his way back in time. So we're switching to the last two speakers. So the next speaker is going to be Stefan Buschka, who's going to be talking about interesting stuff regarding network analysis of encrypted VoIP communications. So Stefan.
Yeah. Hi. Oh. I didn't say anything, so. So I remember the first talk actually. So he talked about old guys. So I'm one of these old guys doing old stuff. Actually, the stuff I'm doing comes from many centuries ago. If you look into the math, or 1950s, and it actually got applied now to encrypted VoIP communication. So what we are talking about is actually music. Any musicians here play guitar? Cool. Then you know what I mean by this thing. And then anybody into signal analysis, filtering, analog digital filtering? You. Cool. So you know what an IIR filter is? FIR filter? Okay, good. So, let's go in medias res. So you will hear only a bit about me and my group. You get a short introduction, a crash course into traffic mining. So I feel a bit lost here, because I'm not a real security guy. So partly, I'm a miner, data miner. I go in really large data sets, and I'm troubleshooting things. So there are people here who like to break things, I like to fix things. Then about the engineering approach we tried, and then about signal analysis, and then some results, and then you can ask questions. So, actually we started off in an operator. We built a small group, so you saw it here, you see it here. A really small group, like in the end 14 people. And we did all kinds of interesting things. And also 1/3 of our task was to troubleshoot large operator systems, something like 18,000 customer routers or GSM things. When something breaks, how to figure out what's going on. So we really stuck together, and you might be possible to identify who I am. So glasses, the guy who's yelling around. And then one guy had the idea to draw a red line, because they were really funny guys who didn't do much from our perspective, like marketing guys and these things. And then the strategy, which you see on the left side, wasn't so clear as well. So we changed in the end. And more or less the same. Also the guy with the glasses there. And then we have some loony guys who do funny experiments. And we do some of Apollo projects. So Apollo projects are like when these astronauts went to the moon, or they should go to the moon, and they didn't know how. So we get some tasks, and we don't know how we can solve them or do them, and we just try it. So some of these are network troubleshooting. So how do you figure out in really large networks when they go down, or how do you figure out what is there if people do not know, and a lot of operators don't know what they actually have. So we build tools, mostly based on like math or statistics. One is, you see the t-shirt, Trendlyzer, it's open source. And the other one is when you get large data, such as something like TCP dumps. What's the largest TCP dump you guys saw? Can you tell me? TCP dump, anybody knows what that is? You smile? No? Something like in Wireshark. Something like 2 mega, 10 mega. Yeah, something like that. So I start with a tera, 10 tera, 20 tera. And then you get these kind of data, and then, okay, go figure out. And there because there was nothing around, we built our own tools. And the next thing, you get something like 10,000 dimensions. So how do you understand this? I mean, I can only do 3. I have my trouble with the 4th at the time. And there's in physics a theory, 10 dimensions. The people were fighting about, no, they are 11th. So how can you make people understand that? And that's what you see here, which is really nice to look at. It's actually useful. And it's also partly open source. And then we did automatic protocol learning. So you have 2 machines. They talk something, we just listening. We automatically reverse engineer the programs who talk this protocol. And then we do some stuff, these experiments, with genetic algorithms to build some really nasty stuff. I cannot talk about that here. So one was actually SSH command guessing. So SSH is encrypted. And so we actually built something where we're just listening in, we get the dumps, and we guess his commands. And we know it's him, it's not him. That's possible, although it's encrypted. Or in IP tunnels, people ask me, what can you tell me when there's something like an IPsec tunnel? Can you tell me what are the applications in there? How many people? What's the profile? It's possible as well. Same story, encrypted void guessing. So we took the hardest, Skype, and actually the feds, I'm working in Switzerland now at this company of work, before I did an operator, and they asked, the pedophiles, they're getting smart, they're using encryption now. We cannot actually guess anymore whether somebody might be a pedophile or not. But it's impossible to guess anything, content in Skype. So this is what I will talk about here, that these impossible projects and how to make them possible. So traffic mining. Traffic mining is data mining in traffic, actually in dumps, or on the Ethernet interface as well. And if Ether has an application in security, as you will see today, then network usage, for instance, figure out what kind of traffic that is, or what is the intent of somebody. Then profiling marketing, we had some jobs in there to figure out, something about users, and whether you churn or not, or these kind of things. And then law enforcement to get indication of evidence. And what we are doing there is actually, you have this stack with organizations and people, you have the user, you have the application, hardware, and operating system, and you listen here. And you do not look in content. You only give me the header, for instance, and I try to tell you something about the organization, user, application, intent. Whatsoever. So, this is the packet. That's what we look at. Does anybody know what kind of packet that is? I mean, your security guys. You know, here these young guys. You know? Is it IPv4 v6, IPv4? 4, why? Oh, yeah. Does it have options, IP options also? No, it doesn't. It's 5, 4 times 5 is 20. No, IP options, sorry. But we highlighted the, so you need to know your thing. Yeah? So I'm not good at IP version 6. I think IP version 6 is evil. So IP version 4 here. So you see the content, the payload. And it is encrypted. Yeah? Or you may look at it. So encrypted payload has a high entropy. So a lot of mess. So if somebody asks you now, I take boxes, I put elephants, mince them up, take cats, mince them up, take hamsters, mince them up, put them in boxes, and shove and just push them over this table, and you have to tell me what's in there. And you only have spaghetti in the boxes, you only see the box, and you see them once. How do you do that? Does the content count, actually? If it's spaghetti? No. You said no. That's right. Because you can't read it anyway. Yeah? So you can do a lot of cryptology, whatsoever, but the task is, you see it once. So you see the packet, see the next packet, and you actually have to figure out what are the features I'm looking to. So what kind of features? Do you have any idea? What kind of features? So when you see the boxes? Timing, yeah. How about color? Huh? Or size? Or the sound? It creates fiction, so when I push it, and when it deaccelerate, maybe that has information. So you look for parameters with high information here. When I take other boxes, who always have this capability, now always have a certain sound or something like that. So the content is actually not important anymore. And the blue stuff, not really. So how do you figure out what are the parameters you need to listen to in order to find out what's there in this minced meat? And when I really mean, I ask you, what is the birthday of the elephant? And it's possible to figure that out. I mean, you young guys, you have all the means to do that, you know, you have the internet. So, if you look just on these numbers, you will end like that. That leads nowhere. So what is the task? Let's have a look. I mean, there's some math. I will explain it. But you have a tunnel. And I give you a lot of trains now in the tunnel. And the question is, what is the load in the tunnel? Our elephants, hamsters, whatever. What kind of train? What is the paint on the train? What's the load? Is a commuter train? Yeah? What kinds of questions? Is there a politician on the train? And you have hundreds of trains in that tunnel, and now you listen to it. You see these gaps, there are gaps in these tracks, and then you hear the wheels going over it, and it goes da-dum, da-dum, da-dum. Heavy train, da-dum, da-dum, da-dum. Fast train, da-dum, da-dum, da-dum. And you only listen to that. That is it. And I asked myself, can you do a theory about that? So I'm coming from physics, so I said, okay, I measure the force there. I cannot look at the train, I see nothing. So I measure the force, and it's the first derivative of the impulse. So maybe you guys know from math, you have to differentiate every parameter, so it's the differentiate in the mass and in velocity. And now we do something. We just say all the trains have the same speed as on the internet. Yeah? All the packets have the same speed, so gone. The next thing, we'll concentrate on that on that term. And now, if there are any mathematicians, look away. We just expand with something like packet. We get two terms here. And here we have it. The mass change per packet length, the packet per time, packet rate. So the packet fire rate. So here we have a motivation. Why these are the parameters we should look at. That's the packet length and the interdistance, how packets are fired. Done. That's it. That's the only thing what you need to look at and you need to work with. So if anybody has trouble, ask me after. No trouble, explain everything. But somebody said we don't have time. Good excuse. So why did we choose Skype? All the others were too simple. At that time, there was a really interesting codec called Silk, which came out, which was from Google, which was not documented at that time. So we thought, let's try that. And Skype has the challenge of a constant packet flow. So not like the others, when the speaker doesn't speak anymore, no packets. So it's easy to see where a sentence ends. That's really too easy. No, you have a constant packet flow. And yeah, then there was this question in 2007 from the Fed, so we said, why not do that? So now we're doing the exercise. Now I will pick somebody. With glasses? Yeah? Ah, yeah. Okay. What do you see? You see here the time, and you see the packet length. We now two parameters are important: the packet length, or the size of the boxes, and how I shift the boxes of the table. So what do you see? I only need to explain. The green is peer-to-peer, two parties talking to each other, and blue is somebody talking to the rest of the world. It has interruptions. Which ones do you mean? The green ones. Which ones? The up there or these ones? Huh? Anybody else? Idea? No idea? What do you see? Do you see some regularities? Do you see some regularities? And look here. These green dots. Oh, thank you very much. Yes, absolutely. So that's actually what you see here. The green was the first Skype detector from Skype 1. When people said it is impossible to detect Skype. Minimum packet length Skype. Minimum packet length 3. Every other application at that time had 4, 5, or 0, or whatever. Skype was the only one with 3. Funny, just by looking at it. Yeah? And the next what you see is, you see here something, a line, and then some wobbling thing, and up there also a line, and then you see these green dots coming down. So that's ping, minimum packet length 3 from Skype. Are you there? The super node, ping, codec training. Oh, we have codecs. And codecs have a certain characteristic. They like actually to optimize the quality of the voice going off the wire. So they adapt. What you see here is codec adaptation. And there you see me, coming from northern Germany, Fischkopf, talking from a Linux computer. And there is a student coming from Bern, talking a bit slower, as you see. So I have more dots up there. So I saw at that time, I can tell what kind of operating system it is. And it's UDP traffic. And there's some information in the packet length. So that's what I saw at that time. That's it. So, we have hypothesis now. First. Now I have to start differently. Somebody writes a program. Really smart guys, these Skype guys. and they change it. So what we want is something that is an invariant. However you change the program, I always get you. I always detect you. I always can apply my method. What does not change? What does not change? So you write your Skype now. You write version 1, version 2, version 3. What does not change? Yes, thanks! And our ability to tolerate delay. So if something above 150 milliseconds or 100 milliseconds, we cannot tolerate that. So they are codecs. So these guys use codecs. So when you go after, all these code and things, don't do that. The invariant to look at here is the codec. And they cannot change it. They do not want to change it. So, the first hypothesis, is there a transfer function between the audio input, me speaking or you speaking, oh, now it's better, and the observed IP packet features, such as packet length and enter distance? Question, is there? Yeah, we saw an indication, but how good is that? And then, can we predict the output? The next is, given the output, can I estimate the input? So the output is on the wire. Just the Gauge block you saw beforehand. Can I do that? Parameter of influence are basic signals. So if anybody worked in engineering, when you have a black box, how would you figure out what it is? So you put it in pulse in there, you do frequency sweeps, all this kind of stuff. Then we know words, humans, phonemes. Phonemes build words, words build sentences. That's what we know. So, and then when you do these kind of things, don't make it too complicated because it's already complicated. So, we say now, everybody uses Skype. And everybody who uses Skype is a human. So there are no aliens. So we assume there's a human sitting there who has a fair understanding of human languages, so no donkeys, no nothing. Then we concentrate on UDP, because if you go to TCP and if you go to proxies and all this kind of, it gets complicated. We first wanted to show proof of concept. And then everybody speaks English. As we figure out here, everybody speaks English. And everybody speaks English over the web. So we don't start with German and Swedish and all this kind of stuff. So we have this setup here. 2 laptops, and in between, packets firing with all kinds of nonsense in it. So, chapter 1, engineering approach. If the audio codec is the invariant, then what's coming in between? So there's the codec, there's a lot of software, there's the IP stack, and then it ends up on the wire. So it changes it something. So the question is, can we understand that? Then there are different sound cards. What do these sound cards do? Then there's software. Everybody runs software, right? And software interfacing you, and then interfacing operating system, and these kind of stuff. And then, when you want to figure something out, you have to put in signals, and you won't believe it, there's also software for it. So you can say, put a rectangle into it. And the software does it, feeds it, and how good is that? And we figured out very bad. So we went old school, took a generator, applied the generator, did an impedance matching, and then fed it into the sound card. Much better. Don't trust these software generators. Old school. So it looks like that. You try to figure out, you do a ramp, and you see at the end one, something. Or you do a frequency sweep and see it's lower, higher, bigger, and then you try to figure out a transfer function. And then you understand the system, if everything is linear. Okay, it isn't. So I just don't show you all the things we did. It was really painstaking. And then we saw when we did the frequency sweep, you actually expect something like that, a line, something simple. It was something like going like that. So that was one reason why we gave up the engineering approach, because we saw it's more complicated than we think. And I like simple things. Yeah? And it's not linear, so when you put the linear frequency sweep in it, so there's no really linear correlation between packet size, for instance, and frequency change in time. There was a hope, didn't work. So there are much more things, I don't bore you with that. The result was, actually, we got a model of Skype. And that's, imagine there are buses, and there's somebody pushing payloads, for instance, minced animals or something, and then they have a certain interdistance here, these buses, and they go with a certain speed, and this conveyor belt goes with a certain speed, which loads the payload into the buses. And so that actually explains what happens, because sometimes one packet lands in the bus, in the container, and sometimes 2 or 3, or sometimes none. That's the whole thing, and that pretty much worked. And that was something like 1 month of painstaking experiments how to with this approach there, this approach. And then we said, okay, what can we learn from that? What can you learn from that? That you now know, oh, that's my model of Skype. Oh yeah, now you can learn from that. You see, okay, that works now that way. It's not that simple. So let's give up, go down, drink beer. Yeah, that's one thing, okay. The physics approach, or anybody engineering approach, anybody idea? You? No? No idea? Okay then. Chapter 2, mining. Yeah, okay, data mining. So, engineering approach didn't work so much, so good, because the model is too complex. I did a very simple model, but it didn't really help. I couldn't map what I see on the wire from the packet interdistance, packet length, back to the speaker, or what he spoke. So, okay, the black box I showed you is obviously not linear. It's obviously very complex. And one thing is, you make now a model of the sound card, you make now a model of all the TCP/IP stack, all the software. It doesn't really make sense. So why don't you take the software itself, because it's there, and try to make something what we call a hidden model. So you don't care how complex it is. You take something, a classifier, some artificial intelligence, and give some input to it, give some output to it, and say, okay, you learn that. I'm too stupid for that, you learn that. Sometimes it works, sometimes not, if you don't do good pre-processing. So the task then I gave was find the mapping. Output, packets. Input, language, speak, English. And find something, phonemes, words, sentences. Find the mapping there. Produce invariants. Show me whenever Skype, all the versions which might come in future, I have to take these invariants, they don't change. I train the model on it, and then I can say, I'm looking for that sentence, and then the model tells me, whoop, there. Something like 80–90%, there's the sentence, or there's the word, or well, there's the phoneme. So we're looking at these kind of signals, packet lengths, over time. So what we found is, now it's again a bit mathematically, let's say the phoneme is pleasure, like pleasure. And it looks like that. The packet signal, time, and you see something like an attack, yeah? Then a comp, then a decay, sustain, release. ADSR curve, well, there are some musicians here with synthesizers, similar thing. And so you see, oh yeah, that's cool. Now we can actually see, okay, we have this attack region, we have a comp, then we have a decay, we have some sustaining packet length, and then release. So we can say, there's the phoneme starting, there's the phoneme ending. And the hope is now, oh, we can train a classifier on this comp up there, and maybe on the sustained decay, and that's characteristic for the phoneme. Okay, let's try that. In order to do that, you have 44 phonemes, and then you have to try out every other combination, and then you have to do a mapping, that's called homomorphism. You have to prove these two things. That's a lot of work. So I said, I don't do that alone. Benoit Dupasquier, student, go do that. Easy, why should I do this shit? So, the result. Now didn't work so good. I mean, it worked if you put more work in it, but we didn't have so much time and money spent on that. So what we saw really, again, the signal, packet length, correlates to silence or signal. That's trivial. Okay, we knew that beforehand. But actually when you have a constant packet train, the length, that's actually good news. So we have a chance. Then word construction from phonemes. So if you have the hope that this signal, actually here, you take several phonemes, build a word, cool, done. I can identify words. Doesn't work so easy as well, because they overlap, they fuse, really complicated, because of the model I showed you with the buses, these kind of things. And then the silence estimation. That's really tricky, to figure out when in this noisy stuff, when there is silence. And that's one important thing. You need to know when there is silence. So you have to estimate that somehow. And it got better when we got more phonemes, words, and sentences, and the longer the word is, the better we could estimate. Right? Sounds trivial as well. So what we said in the end, well, let's do sentence detection. Because that's the lowest hanging fruit. Let's try that. So we got sentence signals. I don't know whether everybody can read that. That's a sentence before prevented them from arriving on time, really. Yeah. And so we got a speech database from a guy who did speech recognition. We're really glad that we got it. And then we had independent speakers, something like 150 to 200, and we did the experiments and figured out, looks the same, great, cool. I didn't think that it's that easy. That was at that time, in 2008, 9, was new Skype version. So actually when we have independent speakers, it looks almost the same. When the signal, when we have different speakers, you can see that, different length, different signal. So for instance here, 2 peaks, they're 1 peak. That's it. Fairly easy. I mean, you do so much complicated stuff. Yeah? I do really easy things here. I show you some signals and say problem solved. So we have 2 sentences. I put the bomb into the tray. The thing is a timeless sculpture. Yeah, cool. So we tried all different combinations and sentences. And then we thought, okay, yeah, but now here's the task. Stop talking, build a classifier for that. So how do you do that? Anybody heard of dynamic time warping? No. Has nothing to do with Enterprise or Star Trek, actually. It's an algorithm. Hidden Markov models. No? Okay, anyway. Yeah, you? Cool, cool. It was before hidden Markov models, actually. Let's put it that way. You want to compare 2 signals. How do you do that? When they have different length, yeah? How do you do that? I mean, what would be the first idea how to do that? Difference, yeah. Yeah? No idea, no. I mean, the first idea what you would get, you look at that as a human, you say, okay, I have to build a machine who figures out that these are really not the same. Okay, let's start on the left, right? Okay, we go on the left. and say, okay, 49 minus 46, there's the difference, 2, 3, 49, 46, 3. Okay? And then we go next and build a difference. Cool, good. Doesn't work so well. So we do it differently. We take the squares and then we take the difference from one point to all the others in time. Next point to all the others. That gives a matrix, huge matrix. Sounds complicated, goes with n squared, but works. So we figure out how do we need to stretch this signal or stretch that signal, that's better. How do we need to stretch it that most of the points here of the signals match? And then we build a distance, like a distance from you and me. So you're farther, and he's closer. So I pick him, right? Good. That's the whole thing. And then you get these maps, and they look nice. Yeah? So that's the matrix. So the more blue, the more closer it is, and the more red, the more different these signals are. So what you're looking then for, what you calculate, is the minimal path. So which is blue? So we find actually a line, and we figure out these two signals are the same. You just have to believe that here. So if somebody wants me to show him how to calculate that, no big deal, I show him. Yeah? I take the whole evening, I explain that. So the next thing is, we have here two different sentences, and now it's all red, all different. And now what you like to find is somehow a path to tell me how different the signal is. And if it's really deviating from the diagonal, and the distance from the diagonal to the signals tells me how different the sentence is, how different the signal is. And here, when you see the diagonal, now you don't see it, but imagine, and you see the difference is big, so this sentence is different. Just take it, okay? Here, same sentence, different sentence. A lot of blue, only red. Done. This is what we did on many words, on many sentences. Poor Benoit. So I made him do this all over the place. So we wrote programs doing that. We tried all combinations. Yes, and then we came actually up with a classifier. We could, when you played something, we could figure out there with a certain probability, under certain assumptions, as researchers like to say, there's this sentence in there. Cool. So we showed it, we published a paper about that. We weren't allowed to publish at the same time for some reasons. So we published in 2010 then, together with when Benoit went to Belfast. So he was out of the company and then published. So we could say, under certain assumptions, over 80%, if these sentences are similar, like train or bus, it's only 66%. No? So the next thing is, how do you figure out, this was with one speaker. So I want you all, now in this model, everybody, the whole population of Sweden. Yeah? And then I have to take the whole population of America because, yeah, they speak differently, English. And then the Germans, oh God. Yeah? So, yeah, I'm German. So, how do you do that? So, don't be scared. Don't be scared. Just show it. If this is 0, yeah, and if these parameters time constant, then this gets all easy. You just have to believe it. Does anybody know about Kalman filters? Cool, you know Kalman filters. He's my friend. So we just skip that. The requirements, yeah, we do it differently now. I explained you Kalman filters. The idea of a Kalman filter is to estimate an average of a signal. So you have many signals now, right? Many signals. And I want from you to tell me what's the prototype. So I get a lot of people here tell me what's the prototype. So you come up with a prototype of a man and a woman, which fits the average of all you, man or woman. That's the idea. This is what you can do with Kalman filters in timeless signals. So imagine, and that actually was used at that time to track radar signals of airplanes. So there's Bob and Alice. And Bob, we don't know really the position of them, but they give me estimates. So really unreliable guys giving me estimates of an airplane. And the Kalman filter has to say, at time t plus delta, I want an estimate of the next position of the plane. So you have two unreliable guys giving you information, and you want a reliable estimate of the next position. This is what Kalman filters do. Done. So, example, here we have unreliable positions. I wanted to learn the median, the average in there, the mean. And the other line, you see the estimation. After some time, it actually gets hang of it. So it trains, it learns over time. So you see it. You see many speakers. So you see actually deviations in the packet length. So look at the blue one, look at the green, look at the red one. And what the Kalman filter does after some time, it gets the hang of it. So we get from many speakers, we get one model of a sentence. Next model, next sentence, or next word combination you look for. Train the Kalman filter. Yes, that's bad news. You need many models for different words, for different sentences. Depends what you're looking for. Okay, that actually was a success for us. So when we showed it, then they said, no, that's not possible. I said, here, it's possible. So there's a leak in Skype. And this leak, what I showed you with a bit of physics and math, that it's in the packet distance, how applications send their packets in length and in the distance. We can actually figure out what's in the content. So, why is that? Because this is optimized. Everything what's in a codec is optimized for quality of service. And they don't care about security, because it's not their business. So, if they would use padding, so you pad the packet length according to a constant length, then the packet signal is something like that. If you do the same thing with the interdistance, okay, then it's done, if you could do that. But it consumes a lot of information. You need estimators for that in order to do that, and you need to have a goal for that. Of course, bullshitting me. So that needs some computing power. And this is what nobody wants to invest. But in principle, if you use padding, for instance, like in IPsec, it works. But as we showed in IP tunnels, we use then the padding against you. We do a mapping from the padding we found the function, and then we figure something out. So be careful with padding. But it would be a quick fix. A better one would be random payload, random interdistances. And then this attack doesn't work in. But that uses a lot of computing power. So, what you can learn from that is, whatever you build on the internet, whether you build TV, whether you build something, Borshka is watching you. If you give me dunks, I can guess something from it. I find somehow a way. If I don't, I find students to do the dirty job, and then they come to me, I do the math, and then we build a classifier, and then we somehow figure it out. Just give me 6 months, a year, or whatever. We figure something out, and you guys can do that as well. Because you know now it's a packet interdistance and the packet length, for instance. And there might be other invariants. And all the pre-processing you need in order to do this job is actually in this open source tool, if you look in a certain plugin, it supplies you something like the first N packets, and you can do some experiments. And I really encourage you to try that. So the conclusions. Detection of sentence in Skype traces is possible. And from my perspective, I say now a really bad word, trivial, because we did all this work. Because now we know why it's possible. It's not so trivial actually to identify phonemes at work, words which guys in the USA did. And they invested a lot of work, and then it's possible. But low-hanging fruit, you give me a sentence, we train a classifier, that's it. There are easy mitigation techniques, but be careful. It's not like you pad to a certain length, because then we look somehow, we figure something out, and we use the padding against you. Put noise in. So remember, developers, if there are some developers, if you want to really produce a secure communication, look at the packets. Look at the packet lengths. Look at the packet interdistance. Make a statistics about that. Look at the entropy. And if you're unsure, use that. Take the add first packet plugin, punch it out, train something on it, or you may contact me, and then we make it really safe. Yeah? And then maybe the NSA can't listen on us. I don't know. So, I want to conclude with something, what I showed you about science. That was really cool guy, Carl Sagan, all the cool guys are dead. I mean, I feel bad, actually now. So, science is only a way of thinking. And I teach that sometimes universities invite me, so it's the way of thinking, it's not the knowledge. And the way of thinking I showed you, I hope I triggered something here, especially in the young guys here, is there's always a way. And you as crackers, I'm not a cracker, you always know, and you showed with your car thing, there's always a way. And the same thing in forensics, packet forensics, there's always a way. And you have the mindset actually to do that job. It's not actually the researchers, because they are somehow dumb. You have the mindset, you know the protocols. You know the thing, and that's the basic. Actually, knowing your thing is the first job in mining. The next thing is actually using tools. And the tools, you get the hang of. And I would be so glad if people from this community actually shows them researchers, high-end researchers at the university, oh, you did that. Oh, how did you do that? Yeah? That would be so cool. Thank you very much.
Beautiful to see Carl Sagan quote.
Yeah,
absolutely.
I love this guy.
That's, scientists and candle in the dark, right?
Yeah.
I don't know if you mentioned, how long did this research take?
It was, okay, so the idea was something like 2003, so I actually showed you the path, how I got the idea. You remember the first thing, the first graph with these lines and the dots and so on? Then I knew there's something hidden. Officially 6 months, but we did something like day and night in the last 3 weeks of his thesis. So I was helping, I was doing a job, I was doing math and programming. So the really breakthrough was in the last 3 weeks. Beforehand, we did a lot of work in trying the engineering approach, which I showed, like putting signals in, understanding the model, and all these kind of things. And we had to do it to prove it. No, it's not the way. Otherwise, engineers would come to me and say, Stefan, you didn't try that. No. So, officially 6 months, including training of Benoit and traffic mining and things, but the last 3 weeks with lots of pizza, lots of, drinks and not sleeping, this kind of stuff.
Loads of data mining.
Yeah, I mean, data mining is seeing, as I showed you. The first thing is see. Make plots. Make two-dimensional, 3, 4, 5, 6 dimensional. No, that's, yeah, but we have 2. If you have 10 dimensions, look for Valimeko, it's on the internet. You can actually view multi-dimensional data spaces in 2. It's possible. Yeah, it's possible.
Any questions for
So if you don't have questions, come to me. I explain everything. I know it's a lot. Yeah, I hope I try to explain the path a bit. And I know all the math. It's not easy, but I'm really willing to explain it to everybody. So show it.
Florian has something else he wants to analyze.
Yeah.
I just want to ask you if you're interested in having a workshop about data mining for hackers at the next CCC Congress. That would be great.
I'm actually at the university in Zurich. They invited me, and there was a boot camp, and I prepared some, like you did here, only in mining. I do the same thing what you do with mining. And actually, well, what the message I want to convey here, it's so simple. It's only a very, it's lateral thinking, it's what you guys can do, and I actually wonder why you guys are not coming up with that. But people hire people at the university. So what I like to do, actually, I take 16-year-olds, 17-year-old guys, and I just
mince them up.
Yeah, mince them up. Yeah. Or the first thing, actually that's no joke. The first thing what I give to people is a packet like that. Where is that? Yeah. A packet like that, and I ask them, tell me everything about it, and tell me the color of the underwear of the owner of this packet, and that's possible. And you guys can do it. You guys can do it because you have everything. And when you did that job, you know what mining is all about. It's about seeing and about cheating. It's all about cheating. It's when you look at all these things, it's there. You go nowhere. You have to look outside what you know. You're smart enough. Yeah, sure.
And then you get them to open that box.
Yeah.
Do we have any more questions?
Otherwise, ask me afterwards. I know, it's late. I put a lot of load on you, so. But it's his fault.
It's just a coffee break. It's just a coffee break.
Yeah, okay, but he invited me. It's his fault.
How many words does a sentence need to have to be able to have a reasonable...
So more than 3.
Okay.
More than 3. Actually, if you do a lot of work, and if you painstaking work, and if you have something like linguists, yeah, and what I didn't have here, all these things to estimate the silence, to estimate noise, and the codec, he goes down with the packet length, you have to estimate that. All this estimation business, signal processing business, I didn't mention here. Yeah? If you do that really thoroughly, you can actually identify words, but it's a lot of work. But it's doable. It's doable. But with minimum 3-4 words, you get pretty good results.
Thank you.
So pretty good means 66%. So, but that means that the sentences are really similar. When they are dissimilar in these heat maps, in these heat maps, so these are really similar things. When they are really dissimilar, not many words. It depends on the sentence. It depends on the phonemes in there. And the phonemes fuse. These are masters, they love each other. So some phonemes will fuse. Vocals and vowels, they talk to each other. I don't know what they are doing, but you cannot separate them sometimes, yeah, and that messes up your precision at your recall. So the answer is depends, but if you have 3-4 words, works pretty good. And speaker independence, I try to motivate with the average. That works, it improves. I mean, then you have more than 80%. Next question.
Well, actually, I think we'll go to coffee and
okay,
take questions offline.
Good, yeah.
So we try to keep this very short so we can be done on time. Yeah. So we'll take a 15-minute coffee break. Coffee is served right outside the doors. Thank you.
bära så går vi två på det.